Next up, we have a pretty exciting opportunity to listen to and hear more about Blue Waters. I think Blue Waters is kind of interesting because, as we all know, it's a very large system. It's a very capable system. But for reasons I'm sure we'll hear in a moment from Bill, didn't submit to the top 500. So we're a little unsure sometimes what exactly the performance of Blue Waters is. And so Bill Kramer from Blue Waters is going to talk to us today about the cutting-edge science that they're doing and the exciting things that are happening with the Blue Waters project. So I'd like to introduce Bill Kramer.
Set up here for the presentation. I just want to thank the conference organizers and Adaptive and their sponsors for inviting me here. It's a pleasure to come talk to this group. I haven't been to one of these meetings in a little while, so I'm learning a lot, and we'll try to share some observations that we had with Blue Waters, as well as a little bit about the status and what we've been doing with it. So I didn't plan to address the question that you brought up about what the real performance of Blue Waters is. I can tell you, I know exactly what the impact performance is. We consciously decided not to measure or not to list it. Doesn't mean we don't know what it is. But the other thing is, we have a different view of what performance really means, sustained performance. And our measure for sustained performance is real-time to solution of real applications. So the measure we use, the system petascale performance measure, SPP, is actually 12 different applications running at scale, large scale, that does the complete from the start of the application to the end of the application. All the defensive I/O, all the real I/O, everything it does, pre-start processing, post-processing for that. In addition to a whole set of other metrics that we used. So by that measure, the system is about 1.3 petaflops of sustained performance across all the components of the system, and about a terabyte, 1.2 terabytes of sustained I/O performance. So not only is it a computational machine, it's intentionally intended to be the most intensive data analytical machine that exists in the world today. So this is ready? Okay. All right. So I thought for this group maybe concentrating a little bit more on the resource management challenges that we've uncovered as we go through the roll-up of Blue Waters and getting it now, but also I think it's something that points to the future. And I know yesterday there were some sessions that touched on some of the things as we've already been involved with Prey and Adaptive and some of our other technology partners about these issues at scale that point to the future. I won't use the term, except this one time, exascale, because I think that that's not the right term to use. We're looking at scale systems in the future, but not the way it was envisioned in some of the original exascale programs. So from the National Science Foundation point of view, very similar to the whole philosophy of Blue Waters, is how do we help science and engineering teams do their work in the most effective way, but to do problems that have never been tried before because there was no resource that could be tried. So the biggest, most challenging problems in the world. So the mission of Blue Waters is to cover the entire space of science, engineering, and even non-traditional applications at scale. Things that we don't currently do on our big systems. It's interesting that some of these applications are the ones you normally see in other systems, the traditional usual suspects. But I said about a third of the application teams that have already been approved have been using Blue Waters and the friendly user systems and the early science systems are non-traditional in the sense, for example, of this health application. So that application team had a very big vision. They wanted to understand how disease spreads in populations of 350 million like the United States, 1.6 billion like in China. They want to be able to model that with agent-based simulation. When they came to us a couple of years ago, they were running on a workstation, single processor workstation. And they could model over the case of maybe a month, happened in the past for something like bird flu spreading in a regional area. They want to do that in advance so that they could help deal with disease as opposed to study and understand the spirit of that. So they need billions of agents. So now this application is running on tens of thousands of cores. We were able to help them. They changed their entire framework. They've gone to Charm++ as their runtime system and framework as opposed to what they were using before. So that's one example that's not traditional. Other things like the simulation of earthquakes at high resolution for the entire LA basin, including all the disruptive forces that would go through the infrastructure, the roads, the buildings. That's the earth science, one of the earth science. Climate and weather at unprecedented resolution. And molecular science, for example, we already have a result that is going to be published in Nature very soon, and that takes about a year and a half to do for a science team to get through Nature and things. That result was done on our early science system, then refined. That result is breaking news on how AIDS and other viruses infect cells and how that can be treated pharmaceutically. So something that could not be done before. It's 10 times more higher resolution than was done before in experiment, but it validates the experimental results. So this is just an example of the types of applications we have from the science teams we're working on. Now, one of the things about Blue Waters is our mission is to provide a tremendous amount of resource to a relatively modest number of project science and engineering teams and help them use that resource to accomplish unprecedented results. But if you look here, and this matrix is listed by types of methods on top, the disciplines here, you'll see it's a dense matrix. We don't have a system that can be specialized or only vectored in one or two architectural areas. So that's the motivation and the investment strategy we use for Blue Waters for the science teams. So this is at high level what Blue Waters is. It's not just a single system. It's a set of subsystems and actually, indeed, a whole set of activities beyond just physical equipment in education, outreach, training, collaboration, application development, application improvement, a whole range of other things. So it's actually a very complete project. But if we talk about the physical resources, we have the largest Cray system by about 50% that Cray has ever built. It's an XE6, XK7 system, about 200, almost 300 racks of that system, liquid cooled, and about 1.5, soon to be 1.6 petabytes of aggregate memory, the world's largest memory system, at least any system I know of that's openly discussed. We have a very high performant online storage system, subsystem. That's 26 petabytes of usable storage, about 36 petabytes of raw storage, and it's above a terabyte per second access from the compute nodes to that storage system and also out. Then we have the world's largest nearline data repository. It is robotic storage with tape, but it has some novel things that don't exist in other places. They will. It uses HPSS, but it also has rate technology, so it lowers the cost of ownership by about 80%. So you can store more data with reliability, no single point of failure, and you're saving what it would normally cost you to do that. So that's about 100 gigabytes per second. It's matched to the speeds of the system. And that capacity is just about half an exabyte, 500 petabytes of storage in that system capacity now. And then, of course, going out to the wide area network, Blue Waters in our facility will never be a bottleneck. So currently, we are about 120 gigabits to the rest of the world from Champaign, Illinois, where Blue Waters is. And that will increase next year to about 300 gigabits per second. So this is the physical infrastructure we have. To go into a little more detail about the resources, you see the flows and the types of interconnects, the world's largest, at least at the time we put it up last year, 40 gigabit network. So everything is 40 gigabit on the Ethernet side going out to the wide area. That's also how we have servers moving through to serve our community. We have the external servers that I know were discussed yesterday for running things, although we don't currently have more talk running externally for that, but that's soon to be. and then a very large InfiniBand fabric for actually all that disk I talked about. Coming out of the Cray Gemini high-speed network fabric with gateways as well. So this is kind of our overall environment in terms of how we've connected things together and move forward. If we look at the resources that our job scheduling software, I've talked, and resource managing software, ALPS, Cray's ALPS, have to manage, it's basically all of this. And we do have a theme for water. So our external environment is called SCUBA. Our login nodes are H2O. We have our management infrastructures named AUKUS. So they all have, we made up the acronyms as we went along, but everything has something to do with water. Our test system is called JYC for Jacques Cousteau. So we have that theme. But essentially the external e-server cabinets, and we're managing about 25 to 26,000 nodes. The interlogos processors that we have can be viewed two different ways in terms of numbers of cores. So we talk in numbers of nodes because that's what we schedule, that's what we deal with. We don't split nodes up. But the interlogos processor, if you look at the floating point unit, you have one floating point unit. There are 16 per node in the x86 nodes, the XE nodes. But each one has an associated integer schedule unit. And if you use it in that mode, you get twice as many cores, but you split the floating point resources in half. So if you were to compare, say, something like a Kraken machine that's at University of Tennessee, then we're about 800,000 cores using the integer unit. We think more in the floating point unit, the bulldozer unit, because that's the way most of our applications use it. They're mostly floating point intensive at the time. And then out through the back, and I didn't mention, we also have a pretty reasonable cyber protection environment. So that's what we're managing through our job in resource management. So I talked a little bit about this, the focus on sustained performance, and I'm happy to talk more offline. But this actually came from the National Science Foundation. Their original concept, the original call for proposals for track 1 was only about sustained performance. They never mentioned peak performance. They never mentioned impact or other performance. It was always about 1 petaflop sustained performance. They had their measures when they released this in early 2007. So this project's already been going on for 5 or 6 years. And then we've added the SP to that measure to make sure that we fully were able to support that wide range of science, because those 12 codes that we used came from the science teams you saw me talk about earlier. So we actually drew not only the codes, but the problem sets from those science teams. Said, we're going to build a system that will do this for multiple projects. And actually we have probably already have demonstrated about 8 or 9 different applications running well above a petaflop of sustained performance. But anyway, that's our philosophy, and we have always taken the philosophy that everything we do is from the user point of view. So that's why we talk about the usable storage or the usable amount of resource. So a view from our portal, just a few things. I know it's a little hard to see. Fortunately, this was a time where we took the snapshot and all the systems were up. That's good. And the blue is the amount of our system, the 25,000 nodes that are in use by applications. And you see that there are 2 that are using about 25% of the system at the time we took this snapshot. So large-scale jobs, I'll show you that a little bit better. We also show, here's a breakdown of a strip chart running the jobs here. You can show some of the dynamics of that, and we're starting to make use already with only the friendly user runs that we've been doing since, or services since we've been providing since about January 1st. 2/3 of our scratch storage space, 21 petabytes, is in use at the moment. So it is used in, if you count those integer cores that I talked about, kind of the more standard way that AMD talks about cores for this, it's about 1.3 billion core hours just since January 1st. But the interesting thing for here is what types of job mix do we have? So obviously we have small jobs, development jobs, whatever. But this is as of about 2 weeks ago. Just tracking use. This red line here is half the size of the system. Half the size of the system. And this is the cumulative amount of time used by the system. Hopefully this animation works. Yep. More than half of our usage is above, in this number down here, 2,048, not very big until you multiply by 32. So more than 65,000 cores. Half of our usage is 65,000 cores. A significant amount is above 200,000 cores. So the resource management challenge that we have is how do we operate a system with high efficiency, high responsiveness, when we're really in the mode of doing this type of work on a day in, day out basis. So, what I thought I'd do is make some observations for you and then see where we go from there. But from the experiences that we've had working with the system since last June, in terms of when we got it all together and started to make sure it could actually do what it did, and uncovering some challenges, but also solving many of the challenges. I think that there are a few observations that not only apply to just we got to make sure Blue Waters runs really well, but really apply to all systems going into the future, all those at-scale systems that we'll be providing in the future. And obviously, we're bigger than most today, but 5 years from now, most will be our size today. So these challenges are going to exist for all of us. And I concentrate on two that touch on job and resource management more than others. And these are challenges, I think, that we have to look at. But the key word is flexibility. So we have been in a state where I would say our philosophy as a community for these systems has been very monolithic. We expect tightly coupled synchronization in many, many processors. We expect the components always to be exactly the same. So they always perform exactly the same. And they'll work all at the same time. So we talk about resiliency and things like that. But in our mode of operation for the systems and our mode of application usage of the systems, we haven't changed our underlying philosophy for quite some time. And as we go into the future, that is not going to work, or if it does work, it's going to be increasingly difficult and less efficient. So I'm not talking about splitting things up and all being embarrassingly parallel. I'm talking about really how do we make the applications and methods that we need at great scale, but do it in a way that provides more flexibility in two key areas that I'll talk about, topology and resilience. It has to span in other areas as well, how we run the system, stuff like that. But I think that that's two of the lessons I'd like to bring here briefly today and show you why this is. So the first observation is topology really matters. When we went through, worked with the early science teams, worked with the codes that we used from those teams to represent the sustained performance of the system, one of the things that we found was making those codes aware of the topology and aware of the layouts that they were using throughout the interconnect made a really big difference on performance. In one case, almost a factor of 10. That's surprising to me. You know, you could tweak and whatever. But the fact is that you can get that much improvement by having the code understand and use the topology well is a strong indicator. About half of the codes actually had improvements, not only because we had already tweaked and optimized for the processor, for the node, with the science teams. But then, how do you get to the point where you're really going to go from half a petaflop of sustained performance to 1.3? A lot of that came from understanding and using the topology of the system and having the code use the topology well, as opposed to just randomly. So that's another interesting facet I found out is the code that NVIDIA uses for their Limpac runs actually benefits. The biggest gain is not from using the accelerator. The biggest gain is actually their topology awareness in terms of how they lay out the work throughout the XK node. But this was all done with hand tuning. It was one of those instances as you're trying to test the system and check it out, and you had performance measures that had to be met. There was a lot of time spent in dedicated time to understand how these things work. It was not always feasible in the general workload with many things running to reap the benefits of this topology awareness. But if we're going to be efficient in the future, if we're going to solve the problems that we have to solve in the future, it has to be the general case. It has to be the case of how things are used as opposed to just a special case to get an acceptance done or to meet a measure. So let me give you two examples of things that we've seen. So this is one of our codes. The red down there is our section for the XK nodes, and all the rest are XE nodes. But the green is the layout of one of our large codes. This is about 6,100 nodes for this application. And we use it because it's sensitive to network interference, right? So it's kind of the canary in the cage for things. But it's a nice experimental code as well as being one of the benchmarks that ran. This actually code ran for about 13 days to meet its performance or its science requirement to prove that the system worked. But anyway, in this subset, it's laid out in roughly the same nodes. There's one difference between the image at the top and the image at the bottom. And that is the image at the top has 4 nodes, 2 Geminis, that are not operating. And they're circled here in purple. The yellow ones are our service nodes. And you can't really see it up there circled in white. There was just one Gemini where the code was placed that was not operating. Just that alone, and this was a dedicated time test, so the runs should be consistent. Just that alone slowed the code up by 20%. So, if we know that there's something broken, which we do, and we don't have these broken very often, but in this case, it was actually, we didn't expect it. This was an experiment that uncovered something we didn't realize. All of a sudden, we have to worry about how to map things, not only just have the interconnect, bypass that, because it can route around it. But when it routes around it, it overloads other links, and this code in particular becomes less efficient. So I never thought, this is almost like chaotic, that less than 0.02% of the components being out of service would impact something 20%. So that's one reason. Fortunately, we don't have this case very often, and now we're very careful when we understand that a Gemini is out of service. We can fix that on the fly, but we do it rapidly so we don't have this going on for a very long time period. But we didn't know that. So here's another one that is a different code. This is about 4,000 nodes, multiplied by 16 or 32 as you prefer. But if you look, the kind of goldish items, those are the layout through the torus. And for some reason, there's one node over here. Everything else is kind of blocked reasonably well, and you'd have communication going between them. And one is over there. And the performance for that change just by having that one node someplace else, 30%. So it's certainly worth paying attention to topology. Not only is it, as systems get used, they become random placement because you don't have blocking, but even in these simple cases that are simple examples of the impact of not having, it's not even the impact of not having the optimal topology assignments. Because obviously we have stuff here and stuff there. Optimally, you put it in some kind of other slab, and you minimize the use of the lower bandwidth links. But in this case, only one node, and it changes a tremendous amount. So, we're not talking about getting optimal, particularly in general use, optimal topology mapping all the time. That would mean very, very difficult and likely a big hit on utilization. One of the big things, our goals have to be that we avoid really detrimental topology assignments. And we think that we can do that in the general case most of the time. And if we do that, the codes will run faster, actually get more work through the system, even if there's some overhead in figuring out where this is. So, 2 motivations for topology, 3 motivations for topology. I want to point out that this applies to all networks, so all interconnects. It doesn't just apply to tori. So we have a tori, we're doing these investigations there. But it applies to all types of measurements. I think the presentation on plugins had a similar slide yesterday. So trees, whether they're fully populated, full bandwidth fat trees, or somehow unbalanced fat trees, have the same issues in terms of how you lay out there. You'll see performance. Hypercubes. It's interesting that I have two examples of the new, more direct connect measures. One from the Power 7, one from the Cascade system. They have the same issue. We had studied the Power 7 a lot, and they have differing bandwidths between the three levels of interconnect that they have. The what IBM called LLs and LRs in D-Link. Because of that, you have processors in a drawer. That's the LLs. You have 4 drawers together into a supernode. That's the LRs. Then you have the supernodes connected together. Well, the normal thing was we want to keep everything in first the drawer, but that's not enough processors, 256 cores. And then you want to keep things within the supernode. That's the exact wrong thing, because you stretch the bandwidth on the slowest link there. What you want to do is lay your jobs out in drawers, and then drawer to drawer across the entire system. Something that wasn't planned on when we studied that. Aries has the same sets of issues. So topology awareness is not just for interconnects that have low bisection bandwidth. It's for all of us as we go into the future. So we're very interested. We have programs starting underway with our application teams for performance and scalability through flexibility. The observation is it's harder and harder for applications to scale on systems that will always have limited bandwidth. So we work with our teams and indeed our technology partners, and those include Adaptive and Cray and some others. But we're working with technology partners to try to improve this, not just for our system, but for other systems as well. So what we can do in applications to make them more aware of the topology applies to many other systems. And then maybe we can help the technology providers provide better technology that's more flexible. So one thing is understanding the examples I use, the experiments that we've been running. Another is better instrumentation about what the network is doing, because those examples don't have anything to do with what the network is actually doing. And that's actually a very hard thing to get out. So we're working with Cray, so we have much better instrumentation in the network itself. So we know where the message is going, where the implementation is, and do it in a way that doesn't impact the ability for, the overhead of the system. Better instrumentation, topology-aware resource and system management that enables and rewards topology-aware applications. And then malleability. So if, again, we're stringent and say, I need this number of cores and I want this configuration, we may not be able to have the application run in time until we free up enough nodes. But if the application can express an amount of flexibility, and the system can take that and figure out what is the best way to adhere or to provide that within some range of flexible parameters, both will benefit more. So malleability of applications, malleability of the system. So it's not just, here's what it is, and I'm not going to negotiate with you. So this way of negotiating between the layers of system software and the application to get the best overall choice, and it may be not just for the application, it has to be for the entire system. So it doesn't help as a system provider if I optimize one application great and I hurt everybody else much more than I optimize them. I have to do a multi-level optimization problem to make sure that I'm still being very efficient for my overall system and all the other people on the system while being as efficient as I can in each individual application run. And consistency is a big issue we won't have time to talk about. But my main point is this only gets worse as we go forward. So in some case, Blue Waters is big enough to be uncovering some of these things. I can guarantee that what we see as issues in our network that we can directly identify through the experiments, other sites are seeing, but they just see it as less efficiency, less utilization. So the improvements that have already been made, say, in how the outing in the network goes, how you uncover and react to congestion in the network, all things Cray has done as we brought up Blue Waters. Now apply and benefit all the other Cray systems of not just this type, but actually going into the Cascade era. So that was a significant amount of work through the summer of understanding what happens with congestion so that we get consistent performance. We can still go further than that. But it's an important thing to pay attention to in the future. So the next thing is flexible resiliency modes. We have gone beyond, at least in our opinion, the point where traditional methods of resiliency can be applied. Now, I'm actually pretty amazed at how resilient, how reliable Blue Waters is. So out of those 26,000 nodes, we're averaging about, on node interrupt, about 2 to 3 per day. That's pretty amazing. And that may be software, that may be something that's triggered by the application, that may be a hardware thing, but only 2 or 3. That's much better than we predicted. Same thing, by the way, for the storage system. Very, very, very good. So we're very pleased with that. But that still means, particularly if we're, probability of having an application, particularly if the application is going to run 24 hours, 48 hours, like some of the teams want to do, they're going to hit something, right? Or probability is something. So what are the choices? So the first choice, run again. That was Seymour Cray's choice. If you didn't get the right answer when he didn't have IEEE floating point in his systems, well, you run it 3 times, and 2 of the 3 will probably be okay. And if it fails, you run it again anyway, right? His system is fast enough, you didn't have to worry about that. So that doesn't work. If we have science problems, the one I mentioned, 13 days of continuous running on the entire system to do a turbulence problem. That was part of the acceptance test, but it was a real science problem that had to be done and now is being published. If you're going to run that long, it's hard to rerun again. Next thing, defensive I/O. All the applications have been doing that. We have system-wide defensive I/O, system-wide checkpoint restart, or we have application checkpoint restart. We have reached the point where that's not feasible anymore. Even application-level checkpoint restart is not feasible. The application teams have done a tremendous job. And by the way, to meet that 13-day requirement, we actually implemented in that code, the real science code, application checkpoint restart. I think it failed. It had node failures 5 times over that 13 days. Okay, you put that in. Some teams are amazingly good at overlapping I/O, so it doesn't take much out of their runtime to do that. Other teams can't do that quite as well. But you're still using an expensive resource. The entire I/O infrastructure, in our case, the interconnect, to get out from the compute nodes. So you're sharing a resource with everybody else. You're overloading that, and it's still an expensive proposition because you have to have more storage. You interfere with other traffic on the interconnect. Now, I know some systems split that, like the SGI system splits an I/O and a communication fabric. So there's BlueJeans. So there's ways that architectures are addressing some of that, but you're still spending expensive, and then there's the energy to do it. So that's not feasible as we go forward. Certainly a system-wide checkpoint, the way we used to use it 10 years ago, is no longer feasible. The time it takes, the disruption it takes. There are new research and development for other types of checkpoint restart, memory-to-memory copies, journaling, SSD. Those may or may not go forward, but I submit to you that eventually they're going to have the same problems that we end up with using our shared file systems for checkpoint restart. Because even if you do a memory-to-memory copy, in most cases you're doing that over the interconnect. So, and then you're only using half your memory, probably the most expensive resource on a system like Blue Waters, right? Spare nodes in job requests. So up in the current state of the art on Blue Waters, because Cray did implement for us the ability for an application to say, if I lose a node, don't kill me. The default up until now for ALPS was always, you lose a node, the whole job gets killed. So now is a feature that says the application can say, lose a node, tell me about it, but don't kill me. And then that application can do something different. But But what does it do at the moment? What that does is I got to put a couple spare nodes in that application request, and they're idle until you need them, and then the application redistributes work. Tron++ is probably the best framework that I've seen for doing this. MPI actually, some of the MPI implementations have the capability of doing this, and the MPI standards group is working towards making MPI much more malleable, flexible, and hopefully that comes out in the next release, 3. Whatever. But eventually that will be a way that we can do business. It still wastes resources because those things and those nodes or whatever that is don't get used until they are, and it's not supported well, as I said. Redistribute work among the remaining nodes. So I mentioned one of the teams went from kind of a standard way of doing business to Tron++ because they could redistribute their work. It was necessary because they're agent-based, and the agents have differing amounts of work based on where the disease is spreading. But Tron also can redistribute work relatively easily. You can do that in MPI, not quite as easily, but it takes a little bit longer to run. So what happens then, if I'm an application and I lose a node, and I'm going to redistribute my work, I got to spend time to redistribute my work. I also have to spend some time to catch up to get the work that was out of that missing node. So I'm probably, as an application, going to want to say, okay, I need 10 more minutes of runtime. Don't kill me because the node went down. Not my fault. I want 10 more minutes of runtime. So there needs to be a dialogue between the application space and the resource management space. And then what we really want to see is a shared pool of spare nodes that can be dynamically provisioned into applications that request it and say that they can handle it if a node dies. So we're talking about the only single points of failure really are node failures. Everything else is redundant. You can route through the networks. We have redundancy throughout the entire storage system. So the biggest issue with single points of failure is now node failure. So we would like to see a pool of spare nodes, not too large, because you don't have to over-provision it very much. And probably these may just be idle nodes that you can't fit in because you always have a few of those. And put that back into that application. Let them redistribute their work, give them a little more time to run a short amount to do that redistribution, and let them go on. So this type of dialogue is what we think is necessary, and that's where we think we as a community need to go. By the way, we do know that when we do this type of thing, take a node from someplace else, if we've done a good job, topology-aware mapping, and then we have a node someplace over here, is going to be a trade-off, and we have to figure out how to do that in an intelligent manner, right? But we need both capabilities on systems. So what we need to do this is multiple layers of hardware and software that coordinate the information reaction. So the applications need situational awareness that they don't currently have from our system. What happened? Why did it happen? Let them make the choice of what's best for them to get the science work through the system. That's the main thing, right? Sustained performance, productivity, the science work going through the system. Analysis and understanding what actions are needed. So there has to be enough information so that both sides, the system and the application, can decide this. And having correct actual messages is probably one of the things that is very challenging at the moment. And then provisioning in real time and interaction with those other constraints I mentioned. So in both these two cases, we basically have a big chicken and egg problem, right? Applications don't code this way because there's no system features or facilities that they can use to take advantage of what they can do inside the application space. And when we bring these types of things to discussion with technology providers, often the first thing is, well, no application uses that, so it's not worth our time to create it. So my message is we cannot brute force our way out of this for the future without losing a lot of utilization potential from our system. And both the application side and the system side have to change when we go to scale. So there's a whole lot of other observations, including how we're our views on storage and I/O, information gathering, other things like that, using heterogeneous, both the XK and XE nodes at scale, because everything we do is at scale. But those are for other times. So To wrap up, the first message is we're already delivering on our commitment for sustained performance. You'll see a lot of results coming out of Blue Waters, and not just for traditional computational problems. We very much appreciate the significant efforts that our partners, technology providers, spent to get a system of this scale working in place in the time period. So from the time that we signed the contract to the time that we had the early science system, the biggest resource in the NSF portfolio, by the way, was 2 months. The time we signed the contract to the time we're in full service, which began March 28th when we had our launch, was less than 15 months. That's an unprecedented way of fielding something this large. So we very much appreciate those, and they include Adaptive and our other partners. I'm very pleased that Adaptive and Cray are taking seriously the issues around topology awareness, and they have work underway, motivated, I think, by the things I showed you, and we started dealing with that back December 2011. But they're not just meant to meet our own individual needs, but also the needs of the community. We're pleased that we have the initial improvements in handling failure, but there's a lot more that needs to be done, and we urge not just Cray and Adaptive, who have roles here, but other technology providers and the MPI community to take that very seriously and move forward, and we'll try to urge them on as we can. But the other thing is we're very pleased and in some ways surprised at how encouraged the application teams are in willing to change what they do. If we can go down the path of improving how systems interact with their applications, they are very much willing to change how they do business as long as there's an advantage to them. Better work, less effort, whatever it is. So we're very encouraged with that. And the thing that we need more of is no application team uses only one system. Every one of our application teams are using other systems. Almost every other major provider, their teams use other systems as well. So what really motivates a team to make changes may be a really big improvement on a particular system, like changing their topology awareness because they get a factor of 10 improvement or a factor of 2 improvement, but more so that they can actually expect to be able to do similar things, maybe with a different architecture, topology, or resiliency model, but they can do similar things in a similar way on other systems. So we have to work as a community towards that. And that's it. So thank you very much.